Sure, we are going to discuss reconciliation. Reconciliation is a mathematical equation that defines a sequence of values recursively. Consider these two functions. The first function t of n equals to t of n minus 1 plus n. Here, each term is defined in terms of previous terms. So t of n, it has been defined in terms of its previous term n minus 1. Okay, similarly, here t of n equals to 2t of n by 2 plus n. Here also t of n, it has been defined in terms of its previous term n by 2. Reconciliation is used to describe the time or space complexity of a recursive algorithm. Whenever you have a recursive algorithm, it can be described with the help of what? Recurrence relation or a recurrence equation. So we call these two as what? Recurrence relation or recurrence equations. What is the need for a recurrence relation? Consider this factorial pseudocode. If n equals to 0, written 1, else written n into factorial of n minus 1. What is n factorial? N factorial is n into n minus 1 factorial. Okay, here the n factorial, it has been used, it is using its previous term n minus 1 to define its function. Okay, so that is called a recurrence relation. This fact, whenever a function calling itself, those kind of functions are called what functions? They are recursive function. Here factorial function is a recursive function because it is calling itself, right? Inside this factorial function, again we are calling this a factorial function with its next instance n minus 1. So we are representing this factorial reconciliation of the form t of n equals to t of n minus 1, this n minus 1 plus 1. So this is a recurrence equation for your factorial function. Whenever we have a recurrence function, we need a base case to solve the time complexity or to compute the time complexity for that reconciliation. So in the factorial function, the base case is t of 0 equals to t of 1 equals to 1. What do you mean by this? When n equals to 0 or when n equals to 1, the time complexity is 1. That is your base case. Okay, and when we have this, what is this n? This n represents the number of input instances or the problem size that we offer to our algorithm. That represents our n. T of n represents the time complexity of the particular algorithm. Okay, we cannot have functions like f of n equals to n square plus 1, f of n equals to 3n cube plus 2n square plus 1. These kind of functions we cannot have it in recursive function, because what is recursive function or what is reconciliation? When we have a term which has been defined by its previous term. For example, t of n equals to t of n minus 1 or t of n equals to 2t of n by 2. When we have such functions, when the term has been defined by its previous term, so those functions are called recurrence functions. We cannot have these f of these functions n square plus 1 3n cube kind of functions. We cannot have it in recurrence relation. Okay, we have two types of recurrence equations. One is decrease function, the other one is divide function. As we discussed, the recurrence equation defines a sequence recursively. Okay, let us see the decrease function. So decrease function, it would be of the form t of n equals to t of n minus 1 plus n for n greater than 0. We need to specify at what value of n or above what value of n we have this reconciliation, and always, as I said, we need to have the base case also. So here the base case is t of 0 equals to 0. The base case may vary, it depends on your algorithm, and the reconciliation also may vary based on your recursive algorithm. Here, okay, this t of n equals to t of n minus 1 plus n represents your recurrence relation. T of 0 equals to 0 represents the base case, and here the problem size, it is decreasing by 1. So that is why, say, minus 1. So that is why we call this as what? Decrease function. In the next instance, it will be t of n minus 1 minus 1. Okay, then it will be like t of n minus 1 minus 1 minus 1. Okay, it keeps going. So this is called decrease function. Okay, and coming over to divide function, here t of n equals to 2t of n by 2 plus n, and the base case is t of 1 equals to 1. So this the division happens in the form of n by 2. Okay, n by 2, n by 4 until you reach the unit instance. So even the decrease function, okay, this decrease will happen until you reach the base case. Here in the divide function, the divide will happen until you reach the base case. This t of 1 equals to 1 is a base case or the initial condition. So you should keep doing these iterations until we reach the base case. Okay, so this is another one of the general forms of your divide function. T of n equals to a into t of n by b plus f of n. So here t of n represents the time complexity of your algorithm for a problem size of n, and a represents the number of recursive calls made by the algorithm. How many recursive calls the algorithm has made, that defines your a. Similarly, this b represents the factor by which the problem size decreases in each recursive call. Do you remember your binary search? The problem size, it decreases by what? By 2. So this 2 is your b. Okay, and this f of n represents the time complexity of work done outside the recursive calls. Okay, here it is not inside the thing. This is the outside outside the recursive calls. What is the time complexity for the work done? So that represents your f of n. This is one of the general forms of divide function. We have many other forms of divide function. Now there are three methods to solve your recurrence relation. So once we solve, what we get the time complexity. Okay, the very first method is substitution method. So what is substitution method? So this is the substitution method. T of n equals to t of n minus 1 plus 1. Then what will be the next thing? Okay, t of n minus 1 equals to t of, in the place of n we have to substitute n minus 1 minus 1 plus 1. So we keep doing this until we reach the base case or the initial condition. Okay, so substitute the recurrence relation into itself until a pattern emerges. Okay, so after a few iterations we will be able to see a pattern. So from that pattern we can compute the time complexity. There are two types of substitution method. One is forward substitution and the other one is backward substitution. The second method is a recursion tree method. Here we need to draw a recurrence tree, okay, which represent the recursive calls, and it is used to calculate the time complexity. And the third method is a master theorem method. It is a method for solving recurrence relation only of this form. If you have your recurrence relation of this form, then you can apply your master theorem. Okay, we cannot apply for other forms. If you have the recurrence equation of this form, then you can apply your master theorem. So these are the three methods for finding the time complexity or for solving the recurrence relation. Thank you for watching this video.